All right, the last of our tests for convergence and divergence, the ratio and root tests. All right, take a minute, copy down the terms for the test. Terms must be non-zero. It's a test for absolute convergence, and these are most useful with exponential and factorial functions. All right, so this notation is not new. All right, this is our limit comparison. Looks like our limit comparison. Limit of the absolute value is less than 1. Series converges absolutely. Diverges if the limit is greater than 1 or doesn't exist. Inconclusive if the limit is equal to 1. So if it's inconclusive, we got to go to another test. All right, determine the convergence or divergence of each. All right, so we would start, it has exactly the two things that the ratio test is useful for, exponential and factorial. Limit as n approaches infinity, 2 to the n plus 1 divided by n plus 1 factorial. Okay, dividing by a sub m, we'll multiply by its reciprocal just to save that step. N factorial over 2 to the n. Okay, let's do some reorganizing. 2 to the n plus 1, that would be equivalent to 2 times 2 to the n. N factorial, we're not going to cancel at all. N plus 1 factorial can simplify to n plus 1 times n factorial, and then our 2 to the n stays put. Now that we've done this, all sorts of terms start to cancel. So this becomes the limit as n approaches infinity of 2 divided by n plus 1. That limit is 0. That limit is less than 1. Therefore, we say this series converges absolutely. So the one thing about this test, be aware, it's just the terms need to be non-zero. So your terms can be negative and positive when you use this, and then the absolute value obviously would make all your terms positive. But it's just non-zero terms. All right, next one. So limit as n approaches infinity, a sub n plus 1, so I'm going to replace all my n's with n plus 1, 3 to the n plus 1, multiply by the reciprocal of the original, 3 to the n, all over n squared, times 2 to the n plus 1. Okay, now we start to simplify a little. No need to expand the binomial. And approaches infinity. So we have n plus 1 quantity squared. I see I have 2 to the n plus 1 on the bottom, so I'm going to break this term up as 2 times 2 to the n plus 1 times 3 to the n, all in the numerator. And then I have 3 times 3 to the n times n squared times 2 to the n plus 1. So it becomes a matter of, okay, well, what terms am I going to need to cancel? So that's why, yes, technically, this is 2 to the n plus 2, which would become 4 times 2 to the n. But then you would have to split this up into 2 to the n times 2, and then 4 divided by 2. They just end up canceling to the 2 we have right there. All right, 3 to the n cancels. My other exponential function cancels. I'm left with the limit as n approaches infinity of 2 times the quantity n plus 1 squared all over 3n squared. Now, when I compare those degrees, they're equal degree, so the limit is just the ratio of the coefficients. 2/3 is less than 1. So again, this series converges absolutely as well. So not a difficult test. Something that we've used this before, but now instead of just finding a limit isn't good enough. We have to make sure that the limit is less than 1 in order for the series to converge. All right. n to the n over n factorial. Now the next test is the root test, and that's when we have something raised to the nth power, but we wouldn't use it on this series because of the n factorial. So limit as n approaches infinity, n plus 1 raised to the n plus 1 divided by n plus 1 factorial, reciprocal of the original. Okay, so limit as n approaches infinity. And now I'm going to break up this exponent, so it'll be n plus 1 to the first times n plus 1 to the n, expanding this factorial, n plus 1 times n factorial times n to the n. All right, n plus 1's cancel, n factorials cancel. So now I have the limit as n approaches infinity, n plus 1 to the n, all divided by, I didn't want to break that up just yet, n to the n. Okay, now when you look at this, there's no way that I could cancel n to the n because I can't expand that binomial on the top at all. So when I compare these, though, they're both being raised to the n power. So I can write that with a single exponent to the n. And now when I simplify one further step, this becomes 1 plus 1 to the n power. This is the limit that we've discussed. This limit itself approaches e. E is bigger than 1, so this series diverges. All right, so you are responsible for being able to recognize that limit. You can recognize it from this step as well, but I think breaking it up into the 1 plus 1 over n makes it more recognizable. Okay, the root test, given series, another test for absolute convergence. We take the limit of the nth root of a given series. What's nice is it has the same conditions as the ratio test. If the limit is less than 1, converges absolutely. Diverges if the limit is bigger than 1 or doesn't exist. Inconclusive if the limit is 1. And this works well with series involving nth powers. All right, so we have e to the 2n divided by n to the n. Okay. So I'm going to look at the limit as n approaches infinity of the nth root of e to the 2n divided by n to the n. Now technically you could do this bit of work sort of before you start the limit statement, but that's how the test is written, the limit of the nth power of the series. So this would be the limit as n approaches infinity. Remember, when we take the nth root, we're multiplying by 1 over n to the power of 1 over n. So this becomes e squared divided by n. Excuse me. The limit as n approaches infinity is 0. 0 is less than 1. So we would conclude that this series converges absolutely. All right, and our last example for the video, n plus 1 divided by 2n plus 1 to the nth power. I'm raising to the nth power, so I'll use my root test again. To the nth. This becomes the limit as n approaches infinity of n plus 1 divided by 2n plus 1. Degrees are equal, therefore my limit is a half. This limit is less than 1, so again we see that this series converges absolutely. Okay, that's it for today.